Okay, so we'll get started here. This is one of my favorite topics, favorite chapters. Very exciting to think about for a lot of reasons. Because it's timely with what's going on here in our environment. So here's my question for you guys. Take a look at this picture and tell me what's going on. Why? What is here? What do you see?
I see mountains.
So there's mountains. I get you. What else?
Ice melting.
We see a lot of snow.
It looks like the roads have been plowed.
So there's actually no roads here. What are the lines that you see? What's going on here? So what's interesting is we have a line over on the right, a bunch of lines towards the middle, a big thick line in the middle, another big thick line in the middle. What are you seeing in this picture? Well, I'll tell you what. We'll just hang on there. Think about that picture for a little bit. We're going to move forward and we'll talk, but we're going to come back to this picture and you guys can take a look at it. All right, so what we're talking about is glaciers and erosion, right? And so what are our objectives? You're going to be able to describe how glaciers form. You're going to be able to compare two main kinds of glaciers, and they're pretty easy. And then you're going to be able to explain the process by which they move. And they do really, really move, and it's amazing. All right, so first thing, glaciers. Glaciers are a mass of moving ice. Well, how did that ice get there? Well, here's the deal. It snowed, and then it snowed, and then it snowed, and then pretty soon it snowed, and then it snowed. And then there was this time when it snowed, and it snowed, and then all of a sudden it snowed, and then it snowed, and it snowed, and 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 snowed, snowed a lot. And so what happens is, if you're in a dog pile, all of you have experienced dog piles or monkey piles or whatever you call them, right? And you start to get a bunch of people on top of you. It starts to create pressure, right? Well, imagine pounds and pounds and pounds and pounds and pounds and pounds and kilograms and kilograms and kilograms of snow. All of a sudden, we see a lot of pressure. And that pressure are powerful agents of erosion. Now, basically right now, as we look at our world, about 10% of our world is ice, snow, glaciers. During the ice ages, which weren't too long ago, it was about 32%. And so we see this drastic decrease. Now, the question that everybody comes to is what's causing the decrease in the glaciers? Well, we do know there's not a dispute at this point anymore that we are seeing climate change. Everybody is in agreement. It's no longer this myth. It's no longer this theory that it's happening. So much that we see a lot of different countries coming together now to try and prevent a 2-degree shift in temperature change globally on annual temperatures. So it's happening. Now, where do we see glaciers? They're on every continent with the exception of one. Australia. Interestingly enough, we even see glaciers in Hawaii, which I think is really cool. My father-in-law used to, when they would go to Hawaii, he used to brag about the fact that he could go skiing in the morning and be in the beach and the ocean in the afternoon all on the same day because of Hawaii. Hawaii is really stinking cool. I love Hawaii. So we get back to this picture. So knowing this picture, we talked about this just a couple minutes ago. You guys said, okay, we've got roads of some sort. Not wrong. They're not roads, but there's something going on here. Anybody want to think about this? Huh? Not water. So the glacier is traveling. This isn't water. This is a glacier. This is snow. Yeah, Lucas. So as it's coming through, what's happening is the glacier is scraping the side of the mountain. And as it does, debris is falling off. And when it does, it creates this line on the edge of the glacier. So then my question is how did the one in the right here get in the middle? What does that mean then? That means that there was another glacier here. So each line represents basically the edge of a mountain. So we have what's called medial moraines and lateral moraines. What's a lateral in football? You throw the ball off to the side. So when it's on the edge, it's a lateral moraine. And when it's in the middle, like this one here on the right-hand side, or the one right in front of us now, they're medial moraines. And they're very good at being bulldozers. Glaciers are great bulldozers. And if you look up high on this mountain here in the background, there is a huge glacier there that's no longer touching the field of the glacier, but it was at one time a contributor to this. Here's another example. So you see on the left here, glacier. On the right here, glacier, medial moraine coming through. So basically, how does it work? Well, we have what's called a snow line. What do you think a snow line is?
Line of snow.
It's where the snow is and where the snow starts and stops, right? And so it's an elevation of where we see snow all the time. I've got a picture of Bailey and Taylor and my wife Jody up on top of a mountain, going up a mountain in Colorado. And it's July. And we're having a snowball fight because we're above the snow line. So the snow remains there all year long. And again, if you think about where you're at, elevation of a snow line is different in different parts of the world. Why? Well, if you think about it, in South America or in the equator, the snow line would have to be much higher because of the hotter temperatures. Versus if you were in Alaska, it would be much lower. So, like in Colorado, the snow line is around 10,000 feet. Right? In the equator, it might be as much as, or near the equator, not at the equator, but it might be as much as 12,000 feet. 13,000 feet. So Kilimanjaro, which is not actually on the equator, but it's just off of it. Yeah, same thing. And translate that about 5,500 meters above sea level. All right. So again, if we go to Alaska, it comes right down to the ground near to sea level. By the way, sea level is at 0. Why? Because it's meters above sea level, and sea level has to be at 0. All right, so we call this an ice field. And it's just basically, it's ice. It's sitting there. But the problem is, as it builds up, we form this pressure. This pressure then starts to move. Now, here's the deal. We see mountains and ice all over the world, right? And so it makes sense. It wants to build up because it's cold or it's not melting. And so I just love this picture, right? So what you have here is by the way, let's go back just real quick. Is this an old or a young mountain? It's a real young mountain, isn't it? Because look how crisp and sharp these peaks are. Very young. I don't actually know where this picture was taken, but I love this picture. But if you look at it, what you have here is way back in the right here, you've got this glacier, and you can see it. And what's happened is this glacier is starting to melt, and in the meltwater, it's dumping ice into the glacial meltwater. And so what we see here is a glacial lake. They're called glacial lakes. We'll talk about those in a little bit. All right. So again, at the poles, it's stinking cold. At the equator, not so cold, right? And so we see it being cold year round. So it makes sense that we're going to see glaciers in Antarctica and maybe in the North Pole, right? So think about how that works. Makes sense that we're going to see it there. Well, we're starting to see those kind of decrease. And what are they there for? Because the snow constantly builds up. And so year after year after year after year. Now, don't misunderstand me. We're going to see some partial melting. We're going to see a decrease. Right? But at the same time, it comes back. And so it's partial, but it also changes in form in these crystals and their grains. And we call this fern. So if you see up here at the top, by the way, it's not true. It's not true that no two snowflakes are alike. In fact, there are repeating patterns. I think there's 6 basic or 7 basic patterns of snowflakes that are similar. So you see this snowflake up top, and over a period of time, what's happening is pressure is building on it. And so as the pressure builds on it, it kind of scrunches and gets beat up and pulverized until it becomes this small grain of ice called fern. And fern basically is grainy ice. And really what it means is the true definition of fern came from of last year, or it comes from last year. And so that makes sense when you talk about a glacier. It's just hanging out. It's still there, grainy ice. Now this stuff is awesome because what it does is it is extremely compacted. Well, why? Because you've got all this material, this snow, this fern on top of it. And as it does, it compacts. It's heavy, right? So you hear about people dying in avalanches and stuff like that, right? Why'd they die? Well, a couple of reasons. 1, the weight. 2, loss of air. Gee, that makes sense, right? And so, or they could be, what's the word I'm looking for? Have a concussion or something else. But mostly it's pressure and air. So fern, because of the pressure, ends up becoming this brilliant blue. And so the reason why that happens is because the blue wavelength of light is not able to penetrate into the dense fern. And so why do you see it as blue? It reflects back at your eyeball because it's reflecting the wavelength of blue back at you. So here, isn't this beautiful? I just so want to go here right now. Not that I want to be back in winter, but yeah, it'd be cold. I agree. Hey, one of my dreams is to go to Antarctica. Yeah, it would be 100%. 100%. But you can see how blue it is. So when we look at a glacier, when you got enough, glaciers form. So if there's enough snow, enough ice, we get a glacier. Now, glacial formations, basically, where are you going to see them? You're going to see them where you got snow. Why doesn't Australia have them? 1, they don't have high enough mountains. 2, their latitude and longitude is not in the greatest places. Right? So, not appropriate for them to have huge amounts of snowfall. Right? So, that's why we don't see those regions with glaciers. Okay? There's 2 basic types of glaciers. This is easy. And they mean what they are. You have the valley glacier, which is like, I'm so sure, right? Because they come from the valley. They're too young to know this.
I know. You're
So,
dating yourself, Mr.
I know, like totally. It's a valley glacier, for sure.
You guys
So,
live the 80s.
yeah, like totally. So, Valley Glacier. Look up Valley Girl sometime. Okay, Valley Glacier. So, Valley Glacier, basically it's in a valley. What's it mean? It's on a mountain. It's coming down a mountain. It's forming a valley. So, basically what's happening as it comes down, the ice moves down. Why? Gravity. It's going down. This large, narrow wedge grinding down the mountain. And that's what it's doing. And so as it does, it carves out the mountain. Where do we see them? We see them in the mountains. Gee, that's crazy. No way. Because that's where the valleys are. Like totally for sure. Everybody good with Valley Glacier? Then it makes sense, right? So here's a Valley Glacier. Whoa, dude. Righteous. Right? So here's my question for you. Take a look at this picture. Right? How many glaciers are in this picture? You're going, well, I just see the one there, Mr. Ritter. It's really great. It's awesome. But no, there are not. Not one, not two, but 1, 2, 3, 4, 5 glaciers that are feeding into this one massive stream, right? And so you can see it. And if you look back here in the back, you can see where they start from. And so what's it doing? It's scouring away. It's cutting a V into this. Well, not really a V. Glaciers, when they cut through, are more of a U-shaped. And we'll see that later. But this is basically 5 glaciers feeding into this one. And it's moving down. Now, it looks flat and stable, but it's actually moving down towards the bottom left-hand side.
You would also go there.
Yeah, I would go there.
Probably even more.
Yeah. Continental ice sheet. What's a continent? Big, flat, stinking mass of land. Ice sheet. A big, flat mass of land that gets a lot of stinking snow. Right? Oh, large area. Where are we seeing them? Antarctica, Greenland, some of Iceland. Which I think is ironic that Iceland is called Iceland and Greenland is called Greenland, and Greenland has more ice than Iceland. Okay. So we see a lot of these large glaciers, glacial ice sheets. Again, these continental glacial sheets in these areas. Again, Antarctica is a continent. There's land there. In fact, if you think about it, it's 1.5 times larger than the continental United States, which is huge. But you don't think that. 90% of it's covered in Greenland. If you think about this, that's incredible to think about. 90% of your country is covered in ice, which makes it hard to go sunbathing. All right, so here's my question. The what ifs. What if we melted all the ice in Antarctica and Greenland? Well, this is not good. The water of the ocean would raise more than 60 meters. And it's all fresh water, which would change the salinity of the water, which...
So they could get perspective on 60 meters. What are you talking
Oh, my gosh. So... Alexis, pull out right there next to you is a meter stick. Down, down, down. Right there. Put your hand down straight ahead. Right in the middle. All right. Good job.
Oh, down here.
Yeah, good.
All right.
This is a meter stick.
I got you.
Take 60 of these. There you go. And it's just basically the ruler that I swing at in class. But yeah. This takes 60 of these. That's 60 meters, right? Crazy.
It would be almost like a football field.
It would be like close to, I'd say a good number would be probably 70 yards, 80 yards, I'm guessing. Is that what it is? 65? 65.6. Gosh, you know what? Awesome.
Two-thirds of a football field.
Yeah. Awesome that you did that. That's great. So again, we're talking, let's think about this. Anybody who lives on the coast, the words I would use are, too bad, so sad. Why? Because they'd be freaking flooded. Right? It's like, hey, should have been a boat, right? Then float away. So here is the Antarctic glacier, and basically we have some areas that are mountainous along the one edge here. These areas that are in gray, those are the ice shelves that are on there, but they're actually over the top of open water, and so it's solid over the top of that. The problem is we're starting to see a lot of that ice shelf and that material. The Larsen ice shelf, we're seeing big glaciers break off of here. I'm sorry, not glaciers, but glacial ice. In other words, icebergs. And so, yeah, it's crazy. Now, here's the interesting thing. Nobody particularly owns Antarctica. There's a treaty that says you can't own Antarctica, but they have basically areas of Antarctica that are managed by certain countries. And it is mainly a scientific research area. There isn't anybody just hanging out there just to hang out there. However, if you want a really cool stinking job, I'm trying to think of the person from Pontiac that does this. There's a guy from Pontiac that actually simply, he went from being a maintenance worker to a cook. He is a cook on Antarctica. They're only there during our winter, which is their summer. And then he comes back. He's only there for 5 months out of the year. And he comes back and he has nothing to do the rest of part of the year, which is really cool if you think about it. But it's hard on a family. Just saying. All right. So how do they move? Well, we call them a river of ice. River of ice. It's the river of the ice. It goes walking down the valley. I don't know any more words to this. So I made it up anyway. So rivers of ice. So glaciers are running because of pressure. They move downward and out. Down and out. And so what happens is, as they do, depends on which ones we're talking about. One's using gravity a lot. The other one's using gravity, but it's just basically using pressure. And so, depending on which glacier you're talking about, you're moving at about 100 meters per year. So, basically, again, we have what's called the basal slip and internal plastic flow. Two main parts of it, pretty straightforward. What I want to do is I want to show you. I've got the wrong one here. I'd like to show you an image of a glacier moving. All right, so this is a time lapse of a glacier in Alaska. Here we go. Okay, that worked out real well. Open with. All right, here we go. So, again, this is part of a study that's going on. And what they're doing, this is, I believe, 365 days in the year of a glacier. And you can see how this glacier is moving, but then it just like stops at this edge. And so you have to ask yourself, okay, why is it stopping at this edge? Well, this is the place where the glacier, it's called calving, we'll talk about that in a little bit, is breaking off. And as it breaks off, the dirt and debris and all that other stuff melts in this little area right here, and the heavy stuff sinks to the bottom, and so we see this buildup of material down here. But the ice then floats away or melts into water and goes about its business. Okay, the next glacier. This is kind of very unique that you get to see this particular look, because this is the image of underneath side of a glacier, but the guy is down there watching it, which is totally messed up. It's the coolest thing I've seen in glaciers.
And finally, a large cavity beneath the ice.
I love the idea of what these guys did. So basically what they did is they find this glacier, they find a way to get underneath it, and then they had to figure out how to time it. So what they did is they took this wheel and painted these lines on this wheel, and it was a bicycle wheel on a board, and it was a spring-loaded board. And basically, you'll see they use the board and the wheel to measure how fast the glacier is moving. It's crazy cool, so stinking simple. I love it.
Finally, a large cavity beneath the ice, where a river of melted ice flows over the bedrock. Above Luke is the glacier, 350 feet thick. Here, Luke can measure the movement of the ice with a bicycle wheel mounted on a cantilever.
See this piece of wood? Well, he's got a bicycle
By
wheel.
speeding up his
They just
video
put a
record,
little
we
triangle on
can
it.
see 5 months worth of ice flow.
Le glacier est en mouvement par son propre poids.
As the glacier slides down the mountain, it spins the wheel.
On a à peu près 55
It moves 2 feet per day, or about an inch an hour.
2, et quelques centimètres par heure.
To my knowledge, it's the only instrument that can measure the movement of a glacier.
That is so awesome. And how simple. You guys could have done that. And that's what I love about that. I love that particular video clip. I really do, just simply because those scientists were using real common sense knowledge. And that's why I love that. All right. I don't want to, here we go. So, this is...
How do glaciers shape the Earth? Glaciers are made up of fallen snow that over many years compresses into large thickened ice masses. Glaciers form when snow remains in one location long enough to transform into ice. What makes glaciers unique is their ability to move. Due to sheer mass, glaciers flow like very slow rivers. Some glaciers are as small as football fields, while others grow to be over 60 miles or over 100 kilometers long. Glaciers not only transport materials as they move, but they also sculpt and carve away the land beneath them. A glacier's weight, combined with its gradual movement, can drastically reshape the landscape. The ice erodes the land surface and carries the broken rocks and soil debris far from their original places, resulting in some interesting glacial landforms. One of the most striking examples of a glaciated valley can be seen here in Yosemite National Park. Yosemite Valley gets its smooth U-shaped profile from the action of glaciers. Thousands of years ago, a glacier filled the entire valley. Gradually, the glacier retreated, creating sheared-away mountainsides and a deep valley with vertical walls.
Right, so great example of how the glaciers make things happen and change our Earth. So gotta love that. Okay, here we go. So basal slip, internal plastic flow. So basal slip, basically we've got an area where the glacier is putting weight and pressure, and it creates a slippery surface. And so as it does, this slightly watery, slippery surface creates a slip and slide for a glacier to move down. And so even though there are small barriers such as rocks, they're able to bulldoze through it or even move around it, as you saw in that last video. And so basically as the water flows, it moves stuff, creates the slippery surface, and what doesn't move gets scraped on. And so like sandpaper, eventually it wears it down into nothing. And so basal slip is a liquidy, slippery surface created by pressure. Everybody good there? So internal plastic flow, basically what's happening here is we're seeing, again, forward motion, but it's the crystals inside, internally, that are slipping over each other. And so it depends on where you're at. In the middle of the glacier, towards the top, we're seeing extremely fast movements. And on the bottom, where it's going past rock and going through that, we see slowed down. Why? Because of friction. So again, the speed is not the same. So on the bottom it's slower, in the middle it's faster, and so you see crevasses as a result of that. And we'll talk about those here in a minute. So again, I'll show you that again. When we see the glacier, we're seeing that these are barriers, and so it has to get through there. And as it's moving, depending on where it's at, you can see the speed difference. Again, I just brought that back up to show you again real quick. So, and again, that's the only place I've ever seen where they've measured a glacier. Okay. So in this particular area, you've got this large continental type situation, but it gets into this valley. So when I talk about this, if you have a garden hose and you turn on the water and put your thumb over the end of it, what happens? It creates pressure and goes faster. Well, the same thing. Imagine these two sides of this glacier, this mountain, are your thumbs. And what's it do? It speeds up the process. It shoots it through there. More erosion. Crazy cool stuff. All right, so just to recap, the interior, what's going on? We're seeing movement because of the weight and pressure. Pressure can cause the ice to melt, causing basal slip. It can also cause some issues with buckling, so the top surface, because it flows faster than the bottom, we see cracks build up. We call those crevasses. And those crevasses are large cracks, and they can go quite deep. So basically, if we look at a crevasse, basically it can go all the way down. It can go down 40, 45 yards, something like that. Here are some people that are on top of a glacier, and you can see the crevasse. Notice that some of the people are wearing like shorts and stuff. This is from a cruise ship, and basically they got off the cruise ship, they went to this glacier, they walk around, they're in their shorts, they all think it's fun, and then they go back on their cruise ship. But that's a glacier. Continental ice sheets, basically it's snow, 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 and I refer to it like vomit, right? You throw up on the desk, where's it going to go? It's going to spread out from wherever it landed. It's not going to just stay in this one large pile in the middle, right? And so it's the same process. The glacier pushes forward. It spreads outward from the middle out. So pretty straightforward. And as we do that, we see the ice moving towards the shores in those areas. And sometimes they go out over the ocean in these ice sheets and these ice shelves. And we talked about those in that picture of Antarctica. And when they break off, they are icebergs. So here is Antarctica, and here is Greenland. And you can see on the right, we have the Larsen ice sheet up top. And that shelf is right there. And then the shelf over here on the right-hand side of the, or left-hand side of it as well. So again, that's where the majority of our icebergs come from. I love this photo, right? Because icebergs are really stinking cool, right? So you go up and you're like, hey, too cool, man. I love the iceberg. But what you don't see is what's under the iceberg, right? And so icebergs are really dangerous. Just ask the that really famous guy that was the captain of the Titanic that found out how dangerous they really are. Yeah. I love the scale of this last one, right? Look at the whale next to it. Holy crapola. We call these tabletops, by the way. You can figure out why it's called a tabletop. All right. So we'll go ahead and stop there. We're going to hand out 5.1 review worksheet and the questions in the book. And those are due tomorrow. Great job, and we'll check you on the next one. Thanks for paying attention. You guys are awesome. Have a great day.